Hi everyone, welcome to Mostly Math. Today we'll be using the Gaussian integral to evaluate the surface area formula for the D sphere. Recall from ordinary calculus the formula for the Gaussian integral, the integral of all space of the Gaussian is equal to the square root of pi. Now what we want to do is the same trick that we did in multivariable calculus to square this and then find the polar coordinate transformation. We're going to be doing that instead of 2 dimensions, we're going to have d dimensions. So we just raise both sides to the dth power to obtain our power of pi. Pi to the d over 2 is equal to the integral raised to the dth power. Now we're going to introduce some dummy variables here. We're going to use x1 through xd. We're going to call each integral a new variable, one of these here. There's going to be d of them. So it's going to be everything replaced with dx1. It's the minus x1 squared. We repeat this d times. And you can see where we're going with this here. We can use the property of the exponentials to collect all the dx's together and then put the x squares all in one exponential. So we have pi to the d over 2 is now equal to, I'm just going to write one integral sign for clarity, but there are still d integrals happening here. Got d integrals. And now we have all of the x's in the numerator here. Obviously, I'm just putting the ellipses to indicate there's x1, x2, x3, all the way to xd. And now we're going to do a hyperspherical coordinate transformation, which is pretty cool. But first, let's talk about ordinary spherical coordinates. We know that if we define a radial coordinate, r squared, to be x squared plus y squared plus z squared, then we are going to have the volume element d cubed x to be dx dy dz equal to r squared dr sine theta d theta d phi. So we have a radial part times an angular part, which we can rewrite this as r squared dr d omega. And we can use d omega a lot in quantum mechanics and electrodynamics due to the fact that many integrals depend only on the radial coordinate. So if we knew what the integral of d omega was, we could factor it out. So let's go ahead and show that it's 4 pi. So the integral of d omega is equal to, well, you have phi going from 0 to 2 pi, integrating itself. Now you have the theta integral going from 0 to pi, integrating sine theta. And we get 2 pi times, well, integral of sine theta is minus cosine theta. I'll put the minus on the outside. Cosine theta evaluated at pi and 0. So we have minus 2 pi here. So cosine of pi is obviously minus 1. Cosine of 0 is 1. So this is minus 2. So this entire expression is actually equal to 4 pi, which should look familiar. So we have the surface area here. Surface area is equal to 4 pi r squared. Putting back the r's tells you that the surface area for an ordinary sphere, or a d equals 3 sphere, is 4 pi r squared. And we just want to do the same thing in d dimensions, basically. So for hyperspherical coordinates, sorry, I can't spell, it doesn't matter. Now we're going to define our d-dimensional radial coordinate. We're going to call it x. X squared is x1 squared, and we add them all up until we get to xd squared. And now we have our volume element d dx, so we have d coordinates. This is just dx1 multiplied through dxd. And if we look what we did the first time, we had a three-dimensional volume element. We had the radius to 1 less power multiplied by the differential for the radius. And then we had our factor d omega. Well, it's going to be the same thing here. It's going to be x to the d minus 1 dx d omega d, where the integral of d omega d is the thing we want. We want this thing. We want the integral of d omega d. It's going to be analogous to this, and it's going to compute the surface area of the d sphere of radius 1. We got 4 pi here. We're going to get some other constants here. We want that. And yep, that should be all you need to know about hyperspherical coordinates. Just for future reference, let's write them up here. So we're going to have x would be what we just did. And of course, d dx is equal to x d minus 1 dx d omega d. I want you to be able to follow along because I need more room to evaluate this. And from here on out, it's going to look pretty much like the proof for the regular Gaussian integral. We're just going to have d's floating around instead of 2's and the 3's. But it's really not that bad. Not that bad at all. All right. So now we're going to keep the d integrals here for a second, just show what you got. Okay, we have the integral of all space of d dx e to the minus x squared. We still have d integrals. We haven't done anything at this point besides change to some more compact notation, defining x basically. Now we're going to take the d integrals and reduce them to one integral using the hyperspherical coordinate transformation. We're going to do this first by, so we're going to write this as the integral from 0 to infinity of our radial coordinate x to the d minus 1 power. And we're going to have an e to the minus x squared. That's actually not going to change. And the thing we want to solve for is actually going to factor out, since it does not depend on x. So this is the hyperspherical coordinate transformation. We've reduced what we want, factoring out of a single variable integral, which we know is equal to pi to the d over 2 eventually. So now all we have to do is evaluate this integral. It's really not that bad. We are going to do a u substitution. We're going to let u be x squared, which tells us that x is equal to square root of u. And we have that du is equal to 2x dx, or dx is equal to du over 2 square roots of u. Just solving for dx here and substituting this relation. And this is just an aside. We can keep going. We have the thing that we want, and the limits are not going to change in this u substitution. 0 squared is 0. Infinity squared is still infinity. So we're going to have 0 to infinity of du over 2 square roots of u. Now we're going to have u to the d minus 1 over 2 power, e to the minus u. And we're going to write this one more time as integral of d omega d 1/2 integral from 0 to infinity du u to the d minus 1 over 2 e to the minus u. We're going to use the gamma function definition here. It's pretty important. Gamma function, gamma of x is defined to be the integral from 0 to infinity, some other variable t of t to the x minus 1 e to the minus t. And yep, that's all we need. We can now recognize this as a gamma function. So we're going to have, not quite actually, not quite. I did make a small mistake here. So we need this is not quite correct. The power is not correct. So we need to take the negative 1/2 power and combine it with this u here. So we're going to have u to the negative 1/2. Then we're going to have u to the d minus 1 over 2. And the negative 1/2s are going to conspire here to become 1. Minus 1/2 is minus 1. This becomes u to the d over 2 minus 1 power. So the correct power here is d over 2 minus 1. Now we can recognize it as a gamma function. We already have the minus 1 here as well, which is pretty cool. So using this definition here of the gamma function, pretty straightforward. It's now integral of d omega d times 1/2 gamma function of d over 2. We're done now. We can go ahead and celebrate. And we had pi to the d over 2 up above is now equal to integral of d omega d 1/2 gamma to the d over 2. We can now easily solve for integral of d omega d to b. This is now equal to 2 pi to the d over 2 over gamma to the d over 2. Great. It's an important formula. Tell your friends. This is the main result of the video. We're going to make a table of values to see how this compares to what we know and see what we can learn new about it. But basically the surface area constant anyways going to be 2 times the power of pi times, multiplied by a gamma function. Pretty straightforward. Pretty straightforward indeed. Yeah. So just to celebrate, so this is actually the surface area of a D sphere of radius 1. And we're going to use the fact later that the surface area, if we put the radius back in, it would just be r to the d minus 1. We're gonna use that later. But yeah, we're done now. Now we want to make a table of values with this formula and see what we can do. Want to compute values that we know, see if it agrees. So we'll be talking about circumferences of circles, areas of circles. Then we're going to be talking about surface area of spheres, as well as the volume of the spheres. And then we're going to derive one more result, the hypersurface area, and then the hypervolume of the force sphere, which is impossible to visualize. Don't even try it, by the way. You're not going to like it. This kind of math is not about visualizing anyways. It's about generalizing. All right. Let's go ahead and compute our table of values here. Thought I had a bigger Pikes PM. Here we go. Okay, so we're going to be computing table with D here. We're going to have D equals 1, for example. We're going to have gamma to the D over 2, for example. And we're also going to be computing integral of d omega d. And we're going to be using these formulae. So we did integral of d omega d to be 2 pi to the d over 2 over gamma d over 2. Yep, this is the main result. Indeed, indeed. And we're also going to be using the functional equation for the gamma function. We're going to be using the fundamental relation gamma of 1/2 is equal to the square root of pi. This is just the Gaussian integral in a different form. And the functional equation gamma of x plus 1 is equal to x gamma of x. This is all we need to derive the table. So I'm not going to derive all of it, but feel free to fill in the missing steps by yourself. So d equals 1, gamma of 1/2 is square root of pi, indicated below. And integral of d omega d, well, we're just going to take 2 to the pi d over 2 power. D is 1 here. And now we're going to divide by gamma of d over 2, which is square root of pi again. Pi's cancel. This becomes 2. Pretty strange, you say? Pretty strange. What did we just do? So we talked about a d equals 1 sphere. So this is like you have an origin, and then you have plus 1 and you have minus 1, and you look at the sphere to be this line basically, and any quantity that talks about how much area is in it is just going to be, you know, I get 1 over here, 1 over here. So that's 2. It's pretty trivial. And now we're going to do d equals 2. Well, gamma of d over 2 here is gamma of 1. Gamma of 1 is simply 1. So when we do 2 to the pi to the d over 2, there's going to be 2 pi over 1, which we recognize as 2 pi. Great. Oh, sorry, I wrote the, yeah. 1 goes here, and 2 pi goes over here. So now we're talking about the circumference of a circle. You might recognize C equals 2 pi r from high school. And for d equals 3, we're going to be able to use the functional equation. So gamma of d over 2 here is simply gamma of 3/2, which we can rewrite as gamma of 1/2 plus 1, which is just 1/2 gamma of 1/2, which is the square root of pi over 2. Excellent, square root of pi over 2. Now we just want to get the appropriate factor of pi up top. So we now have 2 pi to the d over 2. Okay, pi is now 3. So I'm just going to stop here since it's getting kind of tedious. I'll go ahead and fill in the rest of the table for you. Yeah. This becomes 4 pi. And now we're talking about a sphere. So we had the surface area of a sphere. I don't know how to draw a sphere. I forgot. How do you draw a sphere? Please leave a link in the comments. Radius r. Maybe you draw a dotted line like this. Surface area of a sphere is 4 pi r squared, as you know. And yep, that sounds good. That sounds really good. We have a new result as well. If we plug in d equals 4, we're going to have 1 and 2 pi squared as a new result. So basically this talks about like the surface area of some hypersphere, which is not possible to draw. Don't even try it. It's like a sphere within a sphere or something like that. It's not possible to draw. Don't draw it. It's not good. But it tells us that the surface area of this is 2 pi squared r cubed, which is pretty interesting and strange. Okay, so feel free to fill in the missing entry of the table as an exercise. I'll be expanding on the table as well. It's good practice to use the gamma functions. All right, so now we want to talk about the d-dimensional volume. Let's talk about that now. So first, let's put the r's back in. So dimensional analysis tells us that if we know the surface area of the radius 1 sphere, we know the surface area of the radius r sphere, since it has to be proportional to the number of dimensions minus 1. So we denote integral of d omega d, now a function of a radial coordinate, to be what we had before, integral of d omega d r to the d minus 1. We have to put the r's back because we have to integrate the surface area to get the volume, and we can't integrate it if there's no variable. So now we're going to compute VD, get it? Not the venereal disease, just the volume. Don't get scared. This is going to be integrating what we had before, coming out as a constant. Doesn't matter. We integrate from 0 to r of a new variable, which we introduce r prime, of r prime to the d minus 1. And just going to be integral of d omega d r to the d over d. We can just write down our formula for d omega d here. 2 pi to the d over 2 are d over d, gamma d over 2. Now we're going to multiply both sides by 1/2 so we can use the functional equation. This is going to be pi to the d over 2, d over 2, gamma d over 2, all multiplied by our radius, r to the d, which is now just pi to the d over 2 over gamma of d over 2 plus 1, r to the d. Excellent. Now we can expand the table, write down the d-dimensional volumes, see what we get. Now we're going to talk about gamma of d over 2 plus 1 and vd. Okay. So we're going to get these values here. Feel free to fill them in as an exercise. I think I've shown you enough that you can do it. Good practice about using the functional equation for the gamma function. So we get 2 pi 4 pi over 3 and pi squared over 2 as the new volumes. Okay, these should look familiar. 2 is just the trivial volume that we talked about before. But we have new ones like volume to be 4/3 pi r cubed. And before that, we had the area as pi r squared, of course. But now we have a new one. We have a new 4-dimensional sphere. The volume is pi squared over 2 r to the 4th, which is quite interesting. And yeah, so we can compute more values if you want. You can get the 100 sphere area, but things typically get less useful as you go up in the number of dimensions. You might want to ask, why do we need this? Why did you just do this? Well, in quantum field theory, you sometimes have to regularize by using dimensional regularization. So you let the number of d dimensions be arbitrary, and sometimes it's easier to do the integrals in spherical coordinates instead of Cartesian. So QFT, we use dimensional regularization. And it's just cool. I mean, if you want to impress your friends, ask them, what is the volume of the 100-dimensional sphere? Do you know it? I almost guarantee you they won't be able to know it. But you will. Just plug in 100 here. You'll be good to go. If you think of more reasons why it's important, there are many. Feel free to put them in the comments and subscribe. See you next time.